Right now, light is hurtling toward you from our closest stellar companion. Born 4 years ago, having crossed 25 trillion miles of void. When those photons finally strike your retina, you will be perceiving 3 stars disguised as a single point. A red dwarf erupting in stellar explosions several times every day. A gas giant lurking in a region where planetary science says worlds should not survive. And in 2024, the James Webb Space Telescope turned its gilded mirrors toward this 3-star arrangement and produced an image that split the astronomical community straight down the middle. A planet that flickered into view, then disappeared, leaving behind a puzzle that may fundamentally alter our conception of what makes a world capable of sustaining life. If this strikes you as staggering, you are in good company. Hit subscribe and follow us in. Brace yourselves. We begin now. The light reaching your eyes at this very instant departed Alpha Centauri during the year Donald Trump first launched his presidential campaign. Let that settle for a moment. While you were swiping through political headlines in 2016, packets of light were already thundering through interstellar vacuum toward our planet. 4 years and 4 months they spent crossing absolute nothingness, covering 25 trillion miles of dark. That is the span light traverses in 4.37 years, moving at 671 million miles per hour, never decelerating, never pausing, cutting through a vastness so immense it reduces the ocean to the size of a puddle. And yet this cosmic companion sits closer to us than any other star in the entire Milky Way. Astronomers measure stellar distances in parsecs, a unit so enormous it makes miles look like measuring the Pacific Ocean with a teaspoon. Alpha Centauri sits 1.34 parsecs from home. To put that in perspective, most stars visible overhead at night are hundreds or thousands of parsecs away. We are gazing at distant furnaces from epochs when dinosaurs thundered across continents, or when Earth itself had not yet taken shape. The light from certain stars began its voyage before living things first pulled themselves from the primordial sea. Alpha Centauri is practically sitting on our doorstep. But here is where the puzzle deepens. Despite being our closest stellar companion, Alpha Centauri charges through space with breathtaking velocity. The entire system is bearing down on us at 14.5 kilometers per second. Every hour, it closes 60,000 miles of the gap. Every day, 270,000 more. In 29,000 years, it will reach its nearest approach at a distance of only 3.26 light-years. Then it will sweep past us like a traveler who never planned to stay and retreat back into the dark, growing ever more remote with each millennium. Simply measuring this distance demanded catching something nearly impossible to see. As Earth traces its annual path around our star, Alpha Centauri appears to wobble against the backdrop of more distant stars. This minuscule shift, called parallax, measures a mere 1.52 arcseconds. Picture tracking a quarter moving an inch and a half from 2.5 miles away. You would need instruments of extraordinary sensitivity just to register the displacement. That tiny tremor, barely detectable even with our sharpest telescopes, allowed astronomers in the 19th century to calculate the distance for the first time, validating what had long been suspected but never confirmed. The numbers grow even more staggering when travel enters the picture. Driving at highway speed, 70 miles per hour, the trip would consume 41.9 million years. A commercial aircraft at 500 miles per hour would need 11 million years. Voyager 1, our swiftest spacecraft, launched in 1977 and presently moving at 38,000 miles per hour, would not arrive for another 75,000 years. By that point, humanity as we know it would almost certainly no longer exist. Civilizations would have risen and collapsed 3,000 times over. Ice ages would have swept the continents clean. Evolution would have reshaped every organism on the planet beyond any recognition. The ancient Greeks watched Alpha Centauri blazing in the southern sky and christened the surrounding constellation Centaurus. But they never suspected it was multiple stars locked in a gravitational waltz. Arab astronomers called it Rigel Conturus, the foot of the centaur. For millennia, humans gazed upward and saw a single luminous pinpoint, never guessing the reality beneath. We now know it is 3 stars performing a single star impersonation. And in August 2024, the James Webb Space Telescope trained its most sensitive instruments on this system and registered something that should not be there. What your unaided eyes show you is a fabrication. When you observe Alpha Centauri from the southern hemisphere, you see a brilliant solitary point, the 3rd brightest object in the night sky. Your visual system cannot resolve what is genuinely present. 2 stars bound in an 80-year gravitational waltz, spiraling around one another at separations that dwarf our entire solar system. And, far beyond them, a 3rd star so dim it requires a telescope merely to confirm its existence. This is Alpha Centauri A, a yellow star nearly identical in character to our own. It carries 1.1 times the mass of our Sun. It radiates 52% more intensely. Its surface temperature reaches 5,790 Kelvin, almost indistinguishable from the star that warms our world. Standing on a planet circling Alpha Centauri A, you would gaze up at a sun so similar to ours that you might momentarily forget you are 4 light years from Earth. But you would never be alone in that sky. Alpha Centauri B orbits alongside it, an orange dwarf somewhat cooler and dimmer than its companion. The 2 stars trace an elliptical dance that brings them as close as 1 billion miles and flings them as far as 3.3 billion miles apart. That minimum separation roughly equals the distance from our Sun to Saturn. The maximum separation mirrors the distance to Pluto. Their orbital cycle runs 79.91 years from start to finish. Humans have witnessed them complete only 2 or 3 full loops since we first distinguished them as separate objects in 1689. A Jesuit priest named Jean Richaud was tracking a comet when something caught his attention. The reference star he was using appeared doubled through his optics. He had stumbled onto the binary nature of our nearest stellar neighbor entirely by accident. The 2 stars sweep around a shared gravitational center with an eccentricity of 0.52. Describing an orbit far more elongated than circular, stretched like a flattened oval. When they near their closest point, the gravitational turbulence intensifies dramatically. Any embryonic planets attempting to form in the space between them would be shredded or hurled into the void. And then there is Proxima. Alpha Centauri C sits 13,000 astronomical units away from the main pair. Neptune orbits our Sun at 30 astronomical units. Proxima sits 400 times farther from Alpha Centauri A and B than Neptune sits from our star. That separation equals 1.2 trillion miles. Proxima requires 550,000 years to complete a single orbit around the binary pair, assuming it is even gravitationally tethered to the system at all. Some researchers still question whether Proxima genuinely belongs to the family. It is a red dwarf, a tiny star carrying just 12% of our Sun's mass and emitting a mere 1/1600th of its luminosity. Its surface temperature barely climbs to 3000 Kelvin, producing a dull crimson glow. You cannot spot it without optical aid, even though it sits fractionally closer to Earth than Alpha Centauri A and B. Robert Innes discovered it in 1915 from South Africa when he noticed a faint reddish star positioned 2 degrees away from the bright binary. What makes this system still more peculiar is what we have actually detected. Despite being the smallest, faintest, and most violently active star in the E system, Proxima hosts at least 2 confirmed planets and possibly a third. Meanwhile, the 2 luminous stars that planetary science says should be excellent at growing worlds appear essentially empty. Decades of hunting have produced nothing confirmed around Alpha Centauri A or B, until August 2024. Most of humanity has never glimpsed Alpha Centauri. The star remains invisible to anyone residing north of latitude 29 degrees. That boundary cuts through Houston, Jacksonville, and the northern fringe of the Sahara. If you live in New York, London, Paris, Tokyo, or Beijing, Alpha Centauri never clears your horizon. Entire civilizations blossomed and withered without once seeing the star system nearest to our own. The ancient Greeks encountered it, but only barely. Their astronomers in Alexandria could spot it hovering just above the southern horizon on crystalline nights. They folded it into the constellation Centaurus, positioning it at the creature's front hoof. To their eyes, it was simply another luminous point in a cosmos full of them. They had no idea what they were actually observing. Arab astronomers knew it as Rigel Conturus, foot of the centaur. Visible more clearly from the Arabian Peninsula and the North African coast, the star remained an oddity. No one imagined it was our closest stellar neighbor. No one knew 3 stars were hiding inside that single point of light. The first pivotal revelation came in 1689. Jean Richaud, a Jesuit priest posted in India, was tracking a comet through his telescope and needed a reference star to chart the comet's movement. He pointed at the prominent star in Centaurus. What greeted him was a shock. The single point resolved into 2 distinct stars under magnification. He had accidentally revealed the binary nature of our nearest stellar system. For 2 centuries afterward, astronomers assumed those 2 stars were the whole story. Then, in 1839, Thomas Henderson measured the parallax from the Cape of Good Hope in South Africa. The result, rough by contemporary standards, revealed something astonishing. Alpha Centauri was the closest star system to Earth. The finding electrified the astronomical community. Humanity had been staring at its nearest stellar neighbor for centuries without grasping what it was. But the system harbored one more secret. In 1915, Robert Innes was working in Johannesburg when something peculiar caught his eye. A faint red star sat approximately 2 degrees from the bright Alpha Centauri binary, 4 times the apparent width of the full moon. Most astronomers would have dismissed it as coincidental. Innes chose to measure its proper motion, the rate at which it drifts across the celestial sphere. The finding transformed everything. The dim red star was moving in the same direction and at essentially the same speed as the Alpha Centauri binary. This was not accident. The red dwarf was a member of the same system, circling the central pair at the staggering distance of 13,000 astronomical units. Innes named it Proxima Centauri because it proved to sit fractionally closer to Earth than the other 2. Proxima is too faint to see without optical assistance, glowing at magnitude 11.1. Binoculars at minimum are required, and even then locating it demands knowing precisely where to look. For all of human history prior to 1915, humanity was entirely unaware that the star nearest to our own was a tiny red dwarf burning unnoticed in the southern sky. This geographic circumstance has shaped how we study the system. Nearly every major observation of Alpha Centauri has originated in the southern hemisphere. Telescopes in Chile, South Africa, and Australia have shouldered the work of exploring our nearest neighbor, the Very Large Telescope, Hubble during its southern passes. And in August 2024, the James Webb Space Telescope, orbiting far above any hemispheric restriction, turned toward Alpha Centauri, and what it discovered has left astronomers questioning the foundations of what they believed. Alpha Centauri A is essentially a twin of our Sun. Its surface reaches 5,790 Kelvin. Our star burns at 5,778 Kelvin. 12 degrees of difference across nearly 6,000 degrees of incandescent plasma. Both carry the spectral classification G2-Va, identical category, identical color, identical stellar fingerprint. Swap one for the other, and you would likely never notice from Earth. But a difference does exist, and it carries weight. Alpha Centauri A is 10% more massive than our Sun. It shines 52% more intensely. Its diameter is 22% greater. These figures might sound negligible, but in astronomy, even small deviations can determine whether a planetary system flourishes or a system remains a barren void. The star is also older, somewhere between 5 and 6 billion years against our Sun's 4.6 billion. And here is where things become genuinely strange. Alpha Centauri A contains 70% more metals than our star. In astronomical language, metals means everything heavier than hydrogen and helium, iron, silicon, carbon, oxygen, all the raw material from which planets are built. This star emerged from a cloud enriched by the wreckage of earlier stellar generations. It had more building blocks at its disposal. According to every principle we understand about planet formation, Alpha Centauri A should be home to more worlds than our own star. Metal-rich stars statistically host more gas giants. The correlation is robust and verified across thousands of exoplanet discoveries. More metals translate to more dust in the protoplanetary disk. More dust produces larger planetesimals. Larger planetesimals means accelerated growth into giant planets. The logic is straightforward. The observations confirm it. High metallicity stars should be planetary nurseries. Yet Alpha Centauri A shows not a single confirmed world. Decades of radial velocity measurements found nothing. Transit surveys found nothing. Direct imaging programs found nothing. 4 years, astronomers stared into a system that planetary science insists should be bursting with worlds and saw only emptiness. The silence grew more bewildering the longer it continued. Meanwhile, Proxima Centauri, a tiny red dwarf carrying far less metal content, harbors at least 2 confirmed planets and possibly a third. The contrast is maddening. Alpha Centauri A sits 100,000 times closer than most exoplanet host stars we examine. A world there would appear 100,000 times brighter than an equivalent planet orbiting a star, 1,000 light-years distant. We could dissect its atmosphere in extraordinary detail. We could hunt for biosignatures, using instruments that already exist. We could track seasonal shifts, monitor weather systems, perhaps even detect the glow of cities if they existed. But first, we must locate the planets. The proximity advantage makes Alpha Centauri A the ideal laboratory for confronting fundamental questions. Why does our solar system carry the architecture it does? Why 4 rocky planets close in and 4 gas giants farther out? Is that arrangement typical or exotic? If Alpha Centauri A harbors planets, how do they diverge from ours? If it has none, why did our star spawn a planetary system while its near twin did not? These questions have haunted planetary scientists for decades. Then, in August 2024, the James Webb Space Telescope swung its mid-infrared camera toward Alpha Centauri A and registered a faint point of light orbiting at roughly twice Earth's distance from our own Sun. A planet inhabiting a place where planets should not exist. Between 50 and 75% of all stars in our galaxy live in binary or multiple star systems. Absorb that number. Half or more of every star you see overhead each night is in reality 2 or more stars shackled by gravity, orbiting each other in an eternal embrace. Binary systems are the standard. Single stars like ours are the outliers. If we intend to understand how planets take shape across the galaxy, we must first understand how they form around paired stars. This makes Alpha Centauri A and B perfect subjects, close enough to study in depth, similar enough to our star to permit meaningful comparison, and metal-rich enough that every theoretical model predicts they should have produced planets. Gas giants especially. The data is unambiguous. Stars carrying 70% more metals than ours produce gas giants at substantially elevated rates. Yet, for decade after decade, we detected nothing. Radial velocity surveys chased the telltale gravitational wobble planets induce in their host stars. Nothing. Transit surveys watched for the slight dip in starlight when a world passes across the stellar face. Nothing. Direct imaging programs attempted to capture planets as points of infrared light by filtering out the stellar glare. Nothing. The silence was deafening. Proxima, by contrast, yielded its secrets with relative ease. Radial velocity measurements confirmed Proxima b in 2016. A potentially habitable world completing an orbit every 11 days. Follow-up observations hinted at Proxima d in 2022, a Mars-sized body orbiting every 5 days. The diminutive red dwarf, despite being far less massive and metal-poor compared to Alpha Centauri A, appeared to host an entire retinue of worlds. Why should stars resembling our Sun be barren while the tiny red dwarf teemed with planets? One explanation is that binary dynamics disrupt the planet-forming process. When 2 stars orbit each other as closely as Alpha Centauri A and B, their combined gravity churns the protoplanetary disk like a spoon stirring coffee. Material that should gradually clump into planets gets scattered, expelled, or ground to powder. Simulations demonstrate that super-Earths and sub-Neptunes form less readily in tight binary systems, though gas giants should still manage to coalesce. Another possibility is that planets are present but concealed. Rocky worlds are compact and faint, difficult to detect even around solitary stars. Around a binary system with 2 brilliant light sources, the detection challenge multiplies enormously. Perhaps Earth-scale worlds orbit Alpha Centauri A, invisible to our current instruments. Perhaps they orbit at orientations that preclude transits, while radial velocity signatures vanish into stellar noise. Or perhaps something darker is at work. Perhaps the high metallicity is a trap rather than a gift. Carbon-enriched stars may produce carbon-enriched planets, worlds with diamond mantles and frozen geological interiors. Geologically inert, unable to maintain magnetic fields, atmospheres peeled away by stellar wind. Perhaps Alpha Centauri's metal wealth sealed the fate of its planets before they ever fully assembled. The mystery endured until 2019. That year, astronomers working with the Very Large Telescope's NEAR experiment detected something intriguing. A faint thermal signal apparently orbiting Alpha Centauri A at roughly 1 astronomical unit. The signal was marginal, hovering barely above the noise floor with a signal-to-noise ratio of only 3. Most scientists remained unconvinced. It could have been real. It could have been an instrumental artifact. Then August 2024 arrived and transformed everything. In May and June of 2019, the Very Large Telescope in Chile attempted something unprecedented. The NEAR experiment, supported by breakthrough initiatives, set out to photograph planets around Alpha Centauri A and B in mid-infrared wavelengths, not detect their gravitational influence, not catch them crossing the stellar disk, but actually photograph them, rendering them as visible points of light against the dark. The engineering challenges were formidable. The binary nature demanded simultaneous management of 2 brilliant stars. The proximity, ordinarily a tremendous advantage, became a liability because the stars swept across the sky so rapidly. The team accumulated 100 hours of observing time across 19 nights. They deployed an upgraded VIZR instrument, fitted with an annular groove phase mask coronagraph to suppress starlight. A deformable secondary mirror corrected for atmospheric blurring in real time. Most ingeniously, they deployed an 8 Hz chopping technique that alternated the telescope's field of view between Alpha Centauri A and Alpha Centauri B 8 times every second. Planets near A would register as positive signals. Planets near B would register as negative signals. Background noise would cancel. The raw data volume was staggering. 5 million images, 7 terabytes. After months of exhaustive analysis, the team found something. A point source they designated Candidate 1, or C1, sitting approximately 1.1 astronomical units from Alpha Centauri A. The thermal signature implied a giant planet with a radius somewhere between 3 and 11 Earth radii, somewhere in the range between Neptune and Saturn. The signal appeared consistently across subsets of the data, but the signal-to-noise ratio remained, only 3. In astronomy, a detection is generally considered robust, only at a signal-to-noise ratio of at least 5. 3 is borderline. It means the signal is 3 times stronger than background noise, which sounds meaningful until you appreciate how many spurious signals random noise can generate. Instrumental ghosts, cosmic ray strikes, scattered light from the binary companion, all of these can masquerade as planetary signatures. Most of the scientific community withheld judgment. The team published their findings with measured caution, acknowledging that C1 might be a systematic artifact rather than a genuine world. They requested independent confirmation. The detection was intriguing, they noted, but far from established. The broader astronomical community agreed. Some dismissed it outright. Others filed it away as interesting but unverified. The signal sat suspended in uncertainty for 5 years. No follow-up campaign confirmed it. No other telescope attempted verification. The NEAR experiment had been a singular effort, and replicating those observations with different hardware proved impractical. The chopping technique was novel and powerful, but fiendishly complex. C1 remained a phantom in the dataset, tantalizing but unproved. Then, in August 2024, the James Webb Space Telescope turned toward Alpha Centauri A. JWST employed an entirely different instrument, a different wavelength band, a different observational strategy, operating in the vacuum of space rather than peering through atmosphere. The team was not attempting to verify the 2019 signal. They were conducting a fully independent search using the most capable infrared telescope humanity has ever constructed. What they found sat on the opposite side of the star from where C1 had been detected. 5 years had elapsed between the two observations. If a planet circled Alpha Centauri A on a roughly 2 to 3 year orbit, it would have completed between 1.5 and 2.5 full loops in that interval. It would now sit on the opposite side of the star. The position matched. The brightness matched. The thermal signature matched. Suddenly, the 2019 detection that almost no one believed looked credible. Imagine trying to spot a firefly suspended next to a searchlight from 25 trillion miles away. That captures the challenge of direct imaging around Alpha Centauri. The stars emit blinding light. Any orbiting planet would be millions of times fainter. Stellar brilliance drowns the planet's faint thermal glow the way a stadium floodlight extinguishes a candle flame. Conventional coronagraphs block most of the starlight, carving out a dark region near the stellar disk where planets might emerge. But in a binary system, there are two searchlights, not one. The VLT team required something radical. They invented binary chopping. 8 times per second, a motorized mirror flicked the telescope's line of sight back and forth between Alpha Centauri A and Alpha Centauri B. The detector captured images, alternating between the two stars so rapidly that atmospheric conditions remained essentially stable between successive frames. This created something remarkable. Worlds orbiting Alpha Centauri A would register as positive sources in the A frames and vanish in the B frames. Worlds orbiting Alpha Centauri B would appear as positive sources in the B frames and disappear in the A frames. Background objects, instrumental ghosts, and residual starlight would appear at comparable brightness in both frame sets. Subtracting the B frames from the A frames canceled everything that appeared in both. Only genuine planets survived the subtraction. The technique was elegant, powerful, and extraordinarily demanding to execute. It required split millisecond precision, flawless atmospheric compensation, and sophisticated computational pipelines to register and subtract millions of frames without introducing new artifacts. The telescope also needed a deformable secondary mirror. Earth's atmosphere distorts starlight as it descends, causing stars to shimmer and images to blur. Adaptive optics systems measure these distortions continuously and reshape a flexible mirror to compensate, effectively freezing the atmospheric turbulence. The visor instrument on the Very Large Telescope employed a deformable secondary mirror, driven by hundreds of actuators reshaping the surface thousands of times per second. Without that mirror, the chopping technique would have collapsed. The 8 Hz chopping rate was carefully chosen. Slower and atmospheric conditions would shift between the A and B exposures, breaking the cancellation. Faster, and the mechanical system could not keep pace. 8 Hz was the operational sweet spot where the atmosphere remained stable and the hardware remained functional. Each observing session involved thousands of chops, millions of individual frames, every one of which required precise registration and subtraction. Data reduction consumed months. Cosmic ray. Strikes had to be identified and stripped from the exposures. Tiny mechanical imperfections in the chopping mirror had to be corrected for slight misalignments between frames. Residual starlight bleeding past the coronagraph had to be modeled and removed. Genuine point sources had to be separated from statistical fluctuations in the noise floor. When the analysis concluded, they had Candidate 1, a faint point source approximately 1 astronomical unit from Alpha Centauri A. Signal-to-noise ratio of 3, borderline but impossible to dismiss. The team published cautiously. Independent confirmation was essential. The technique had functioned, but was the detection authentic or merely noise? 5 years later, the James Webb Space Telescope delivered its verdict using entirely different methods from space. At 4.24 light-years from Earth, a planet traces a loop around a red dwarf every 11 days. Proxima b was confirmed in August 2016, following years of radial velocity accumulation. The announcement generated headlines worldwide. The closest potentially habitable exoplanet to Earth. A world theoretically reachable within a human lifetime if we could engineer spacecraft of sufficient speed. A location where liquid water might pool on the surface. The numbers seemed almost too convenient. Proxima b carries at least 1.17 Earth masses. It orbits at 0.0485 astronomical units from Proxima Centauri, which sounds impossibly close until you recall that Proxima is a red dwarf emitting only 1/1600th of our Sun's luminosity. At that orbital distance, Proxima b collects roughly the same energy from its star that Earth receives from ours. It sits comfortably within the habitable zone. The habitable zone is the annular region around a star where surface temperatures permit liquid water to persist. Too close and water boils off. Too far and it crystallizes. Proxima b orbits right where water remains liquid, provided the planet carries an atmosphere and the right surface chemistry. But physical reality is vastly more complicated than orbital geometry. Proxima Centauri is nothing like our gentle star. It is an M dwarf, a stellar type composing 75% of all stars in the galaxy, yet one that may be spectacularly hostile to biology. Proxima's surface churns with violent magnetic convulsions. Superflares erupt regularly, sometimes amplifying the star's output by a factor of 10 or 20 within mere seconds. These eruptions blast the surrounding space with radiation at intensities that would sterilize Earth's surface within hours. Proxima b absorbs 400 times more X-ray flux than Earth. Proxima b also confronts another obstacle. It is almost certainly tidally locked. When a planet orbits in close proximity to its star, gravitational tidal forces progressively decelerate the planet's rotation until one hemisphere faces the star permanently. The same physics that locked our moon to perpetually show Earth a single face has almost certainly locked Proxima b to show Proxima, the same hemisphere forever. One side of the world endures endless day. The other is plunged into permanent night. On the day face, the star hangs immobile in the sky, pouring down unrelenting radiation. Temperatures climb. Any surface water would evaporate quickly. On the night face, darkness never lifts. Temperatures cascade far below freezing. Water becomes permafrost. The terminator, the perpetual boundary between day and night, might shelter a narrow habitable corridor where temperatures hover at moderate levels, but only if the planet possesses an atmosphere. Without one to redistribute thermal energy, the sunlit hemisphere would be a furnace, and the dark hemisphere a refrigerator with no temperate transition between them. A thick atmosphere could drive global circulation patterns to carry heat from day side to night side, moderating temperatures across both regions. The critical question is whether Proxima b could retain an atmosphere under sustained stellar bombardment. Some models indicate the atmosphere would have been stripped away billions of years ago. Others suggest that if Proxima b formed with sufficient water reserves and sustains a robust magnetic field to deflect stellar wind, a dense atmosphere could persist. The honest answer is that we do not know. We have never observed Proxima b directly. We have never sampled its atmosphere or detected any evidence of water or life. We know it exists only through the infinitesimal wobble it imprints on its host star. Imagine a world where the sky never changes. On one hemisphere of Proxima b, Proxima Centauri hangs frozen in perpetual position. It does not rise. It does not set. It simply blazes there like an unblinking eye, showering half the planet in ceaseless radiation. The terrain beneath this eye has experienced a single unending day, stretching across billions of years, with billions more still to come. On the opposite hemisphere, stars wheel through perpetual night. Proxima never crests the horizon. The sky reveals only the distant pinpoints of other stellar systems, including Alpha Centauri A and B, burning brightly enough to project faint shadows. Surface temperatures plunge to hundreds of degrees below freezing. Any atmospheric gas migrating to this hemisphere freezes solid and precipitates out. Mountains of solidified nitrogen, glaciers of carbon dioxide ice, seas converted to stone. Caught between these extremes lies the terminator zone, a slender arc of perpetual twilight where the star sits forever on the horizon. Temperatures in this strip might permit liquid water, assuming the planet hosts any liquid water at all. This ribbon might constitute the only genuinely habitable strip on the entire world, a narrow ring where life, if it persists anywhere, clings to existence in the dim red light of a star that never moves. Tidal locking is the unavoidable destiny for planets orbiting red dwarfs this closely. The gravitational dialogue between Proxima and Proxima b raises tidal bulges on the planet's surface. As the planet rotates, those bulges migrate across its surface, generating friction that bleeds kinetic energy and slows rotation. Over geological timescales, rotation decelerates until the orbital period equals the rotational period. The planet becomes locked, one face presented to the star forever. Our moon completed this same process billions of years ago, under Earth's gravitational influence. For Proxima b, orbiting far closer to a far more massive gravitational source relative to its orbital distance, the locking process almost certainly completed within the first few 100 million years of the planet's existence. This situation poses severe problems for biology as we understand it. On Earth, the day-night cycle drives planetary-scale atmospheric circulation. Solar heating on the day side generates rising air masses that flow poleward and toward the night side, where they cool and descend. This global engine distributes heat and moisture across the planet's surface. Without that cycle, Earth's climate would be alien and likely inhospitable. Proxima b has no day-night cycle. It has only permanent day and permanent night divided by a terminator. Computational models suggest that if Proxima b sustains a sufficiently thick atmosphere, global circulation could still emerge. Hot air ascending over the sunlit hemisphere would stream at altitude toward the dark side, cool, descend, and return along the surface. This pattern could redistribute thermal energy efficiently enough to prevent the night side from freezing completely solid and the day side from becoming a baking wasteland. But circulation only operates if an atmosphere exists. If stellar wind and radiation have already stripped it away, Proxima b is an airless rock with extreme thermal contrasts between hemispheres. No heat redistribution. No liquid water. No conceivable biology. Just a dead stone spinning slowly through space. One face scorched, and the other entombed in ice. We cannot determine which scenario is reality. We possess no direct atmospheric measurements for Proxima b. We have no temperature readings or surface data. We have only the planet's mass and its orbital parameters. Everything beyond that is inference, and the models paint an unsettling portrait of tidally locked worlds. In August 2024, the James Webb Space Telescope accomplished something that should have been physically unreasonable. Following a failed attempt the previous August, when target acquisition software repeatedly failed, JWST successfully aimed its mid-infrared instrument at Alpha Centauri A. The difficulty was staggering. Alpha Centauri crosses the sky so rapidly that the telescope's pointing system required complete reprogramming from the ground up. The operations team authored custom observing sequences written specifically for this single target. The telescope deployed a 4-quadrant phase mask coronagraph to suppress stellar light. Even with the coronagraph operational, residual starlight flooded the detector. Alpha Centauri b, sitting 8 arcseconds away during the August 2024 observing window, contributed its own wash of scattered photons. The team required a reference star, Epsilon Muscae, to model and subtract the contamination from both stars. Data processing demanded months of meticulous effort. Removing artifacts, compensating for the system's rapid proper motion, constructing sophisticated scattered light models. When analysis finally concluded, they had found it. A faint point source sitting roughly 2 astronomical units from Alpha Centauri A. The object, designated S1, registered at 3.5 microjanskis at 15.5 microns. It shone 10,000 times fainter than the star itself. The thermal fingerprint implied a gas giant roughly the mass of Saturn, with a characteristic temperature near 225 Kelvin. It was orbiting squarely through Alpha Centauri A's habitable zone. This was extraordinary for 3 reasons. First, it would represent the closest directly imaged exoplanet to its host star ever recorded. Second, it would be orbiting within the habitable zone of a Sun-like star, something never before photographed. Third, its temperature and age rendered it the most faithful analog of our own solar system's giant planets among all directly imaged worlds. But the team maintained rigorous caution. Direct imaging is notorious for producing false positives. Instrumental artifacts mimic planetary signals. Scattered stellar light creates ghost images. Background stars occasionally align with the target in ways that suggest orbital motion. Confirmation required seeing the planet again, displaced to a new position that demonstrated orbit around Alpha Centauri A. Follow-up observations were scheduled for February 2025. When February arrived, JWST reacquired Alpha Centauri A. Same instrument, same coronagraph, same careful processing protocol. They examined the precise location where S1 should appear, assuming a circular orbit. Nothing. In April 2025, They tried again using precious director's discretionary time, emergency allocations reserved for observations of sufficient scientific urgency to justify interrupting the standing schedule. Still nothing. The planet had vanished. One of the decade's most significant potential astronomical discoveries had apparently disappeared. Aniket Sanghi, the doctoral student leading the analysis, confronted two interpretations. Either the August detection had been a false positive, an artifact sophisticated enough to fool rigorous analysis, or the planet was genuine, but had retreated to a position too close to the star for the coronagraph to separate it from the stellar glare. Computational simulations offered a compelling alternative. If the planet traveled an eccentric trajectory, tilted significantly relative to the orbital plane shared by Alpha Centauri A and B, it would periodically plunge near the star and become effectively undetectable. Fully 52% of dynamically stable orbits consistent with the August detection would have placed the planet inside the coronagraph's inner working angle during February and April. The planet had not ceased to exist. It was playing hide-and-seek with the most sophisticated telescope humanity has ever operated. Imagine attempting to photograph a firefly hovering beside a searchlight from 25 trillion miles away. That was the precise challenge JWST engineers confronted when they aimed the telescope at Alpha Centauri A. The problem was not merely the overwhelming brightness of a single star, but two of them simultaneously. Alpha Centauri B, though separated by 8 arcseconds during the August 2024 campaign, saturated the detector with enough diffuse light to bury any planetary signal. The team identified Epsilon Muscae as a calibration reference, constructed custom computational routines to model the scattering pattern from both stars, then subtracted it pixel by pixel across every frame. The rapid, proper motion compounded every difficulty. Alpha Centauri sweeps 3.7 arcseconds across the sky each year, faster than almost any other target JWST is asked to observe. The telescope tracked this motion in real time against Gaia catalog coordinates, maintaining pointing fidelity to 1.5 milliarcseconds. The equivalent challenge, photographing a hummingbird in full flight from across a football field while mounted on a moving roller coaster. Then the planned spacecraft roll maneuvers failed to execute. The original observation design called for rotating JWST to multiple position angles, which would have allowed the team to distinguish genuine planetary sources from instrumental artifacts by observing how apparent detections behaved as the observatory rotated. When those rolls did not occur as commanded in August, the standard diagnostic tool was unavailable. The team devised alternative statistical techniques, comparing signal patterns across the detector mosaic and relying on the February and April non-detections to eliminate false positives through temporal reasoning. Dr. Charles Beichman summarized the situation with precision. Incredibly challenging observations. JWST was conceived to probe the most distant structures in the observable universe, not to stare directly at blindingly bright nearby stars. The Space Telescope Science Institute operations team rewrote observing sequences from scratch for this single target. They drove the coronagraph to its absolute performance ceiling, suppressing starlight 10,000 times more intense than the planetary signal they were hunting. From that mountain of custom code and painstaking calibration emerged a single point of light at 3.5 microjanskis at 15.5 microns, a contrast ratio of 5.5 times 10 to the minus fifth power. Translated, the planet was more than 10,000 times fainter than its host star at a separation of just 2 astronomical units. But here is what continues to haunt the community. If the planet advances, even slightly closer during its orbit, it vanishes completely inside the coronagraph's inner working angle. The instrument simply cannot resolve star and planet when their angular separation falls below a critical threshold. The detection window opens and closes according to orbital mechanics that remain imperfectly understood. August 2026 will reveal whether we genuinely captured a planet or whether the cosmos arranged an elaborate deception with our most powerful telescope. When a planet disappears twice, the entire foundation of a discovery begins to tremble. February 2025. JWST swung back toward Alpha Centauri A, this time armed with director's discretionary time, the astronomical equivalent of emergency clearance, reserved for findings critical enough to override the entire observing queue. Astronomers do not invoke it casually. The stakes were sharply defined. Confirm or repudiate the August detection before the observation window closed permanently. The frames returned empty. Where S1 had glowed in August, there was nothing but photon noise. No thermal signature, no point source, just the star and its diffuse, scattered halo. April brought a second attempt under the same emergency allocation. Still nothing. Aniket Sanghi, the Caltech doctoral candidate spearheading the analysis, framed it with practiced restraint. We are confronted with the case of a disappearing planet. Colleagues quietly suggested that S1 had never been real. Perhaps it was a systematic error embedded in the data reduction pipeline. Perhaps the August detection emerged from imperfect subtraction of Alpha Centauri B's diffuse, scattered light. Perhaps the team had consumed millions of dollars and irreplaceable telescope time pursuing an artifact. But Sanghi's team refused to surrender. They turned to orbital mechanics instead, simulating millions of potential trajectories to identify which ones were simultaneously consistent with all 3 observational constraints: visible in August 2024, invisible in February 2025, invisible in April 2025. The simulations demanded massive computational resources. Every candidate orbit had to be tested for long-term dynamical stability under the gravitational influence of Alpha Centauri B, which applies a continuous gravitational tug on anything circling Alpha Centauri A. The results were surprising. Fully 52% of dynamically stable solutions placed the planet well inside the coronagraph's inner working angle during both February and April, rendering it fundamentally undetectable regardless of how perfect the observations were. The planet had not gone anywhere. It had migrated into the stellar glare where our instruments are functionally blind. Think of it as watching a moth circle a streetlight. Sometimes it drifts far enough from the bulb that you can track it clearly. Other times it swings directly in front of the light and disappears into the radiance. The moth has not vanished. You simply cannot resolve it against the brightness any longer. Orbital modeling indicated that the planet oscillates between 1 and 2 astronomical units on an elliptical trajectory with an eccentricity near 0.4. When it reaches periapsis, its closest approach, JWST, loses it entirely. When it swings back out toward apoapsis, it reemerges like a ghost resurfacing from the glare. The universe had not taken the planet away. It had merely tucked it somewhere the light makes seeing impossible. But one more chance to find it remained. 5 years is a substantial interval in modern astronomy, but occasionally it is precisely the right amount of time. In May and June of 2019, the Very Large Telescope executed the NEAR experiment, hunting for planets around Alpha Centauri using techniques no one had previously attempted. The team recovered a candidate they labeled C1, registering faintly at roughly 1.1 astronomical units from the star. The signal-to-noise ratio floated around 3, marginal enough that most researchers logged it as interesting but inconclusive. Without independent corroboration, C1 remained a question mark suspended in the data. Then JWST found S1 in August 2024 using a completely different telescope, instrument, wavelength, and the same target star. When researchers overlaid both detections on an orbital diagram, something remarkable crystallized. The two signals occupied opposite sides of Alpha Centauri A. Dr. Kevin Wagner of the University of Arizona articulated what everyone noticed. When you record a source of identical brightness several years later on the diametrically opposite side of the star, the narrative becomes substantially more credible. The temporal separation aligned precisely with an orbital period between 2 and 3 years. Propagating orbital mechanics forward from C1 in 2019, the planet should have completed either 1.5 or 2.5 full revolutions by August 2024. Both scenarios deposited it almost exactly where JWST found S1. The team simulated millions of orbital connections between the two detections. Fully 52% of dynamically stable solutions fitted both observations while simultaneously accounting for why the planet vanished in February and April 2025. The cluster of orbital parameters centered on the most probable solutions suggested a semi-major axis between 1.6 and 2.1 astronomical units with moderate eccentricity near 0.4. 4 distinct orbital families emerged from the analysis. 2 were prograde, orbiting in the same direction that Alpha Centauri B sweeps around Alpha Centauri A. 2 were retrograde, circling in the opposite direction. Half the solutions pointed toward an inclination of 50 degrees. The other half favored 130 degrees, which is geometrically the same orbit viewed from the mirror orientation. What invested this connection with genuine significance was the complete independence of the two observing campaigns. VLT and JWST deploy entirely different instruments, observing strategies, and wavelength ranges. Any systematic instrumental error corrupting one dataset should leave no trace in the other. Yet both experiments recovered thermal emission at nearly identical flux levels, separated by 5 years and 180 degrees of orbital arc. 2 data points do not establish an orbit, but 2 data points from wholly independent facilities separated by half a decade, both consistent with the same family of elliptical trajectories that begins to look less like coincidence and more like reality making itself known. August in 2026 is the tiebreaker. The planet was never missing. It was orbiting. Computational models reveal that S1 traces a dramatically elongated path, sweeping from 2 astronomical units out to less than 1 astronomical unit and back every 2 to 3 years. At apoapsis, when it reaches its maximum separation from Alpha Centauri A, JWST can resolve it cleanly against the residual scattered light. At periapsis, when it plunges inward, the planet crosses inside the coronagraph's inner working angle and vanishes into the stellar radiance. The eccentricity sits near 0.4. Earth's orbit is nearly circular at 0.017. Even Mars, considered relatively elliptical in our planetary family, reaches only 0.09. An eccentricity of 0.4 means this world experiences wildly varying temperatures and radiation intensities depending on where it sits along its trajectory. But the eccentricity itself is not fixed. Alpha Centauri b, orbiting between 12 and 36 astronomical units from Alpha Centauri A, exerts a persistent gravitational torque on anything circling its stellar companion. This interaction excites what astronomers call Kozai leadoff oscillations. The planet's eccentricity and orbital inclination trade off against each other over millennia. When the inclination decreases, the eccentricity amplifies. When the inclination grows, the eccentricity diminishes. Simulations indicate the eccentricity could climb as high as 0.8 during extreme phases, elongating the orbit so severely that the planet would graze, dangerously close to its star before being flung back outward. The inclination compounds the dynamical complexity. Most planets in binary systems align roughly with the plane of the binary orbit, maintaining mutual inclinations below 30 degrees. S1 appears tilted at either 50 or 130 degrees, relative to the Alpha Centauri AB orbital plane. A steep inclination suggesting this world either assembled within an inclined disk or underwent violent gravitational scattering at some point in its history. Picture the planet as a ball on a string being whirled in wide, irregular arcs. Sometimes it swings far out to where observers can track it clearly. Sometimes it snaps inward and blurs into motion too swift to follow. The string itself twists and oscillates because a second person stands nearby, applying intermittent tension to the entire system. The next detection window opens in August 2026. Orbital simulations confidently predict the planet will be near apoapsis then, displaced far enough from the star for JWST's coronagraph to cleanly resolve it. If it appears at the predicted coordinates, confidence in the detection vaults above 95%. If it does not appear, the team returns to first principles. The universe seldom makes things simple, but it invariably leaves traceable clues for those patient enough to seek them. If this planet is real, it occupies one of the strangest orbital niches imaginable. The habitable zone around Alpha Centauri. A spans from 0.9 to 1.3 astronomical units, the corridor where liquid water could exist on a rocky surface. S1 swings right through this zone, oscillating between 1 and 2 astronomical units depending on where it sits in its eccentric path. For a portion of every orbital cycle, this world passes through the precise distance at which life might theoretically flourish. Except that life cannot establish itself there, because the object is a gas giant with a radius between 1.0 and 1.1 times Jupiter's, and a mass somewhere between 90 and 150 Earth masses. S1 falls squarely in the Saturn mass category. It has no solid surface to stand on, no ground on which liquid water could accumulate. Its temperature averages around 225 Kelvin, cold enough to freeze carbon dioxide but warm enough to maintain methane in gaseous form. The atmosphere almost certainly roils with ammonia clouds, methane hazes, and vast cyclonic systems driven by the planet's internal heat release and the varying insulation it absorbs as it traces its elongated orbit. But here is where the story takes an unexpected turn. Gas giants routinely host moons of significant size. Saturn has Titan, with its dense nitrogen atmosphere and hydrocarbon lakes. Jupiter hosts Europa, whose subsurface ocean is kept liquid by tidal flexing. If S1 harbors satellites of comparable scale, they could be habitable. The planet's eccentric orbit would subject any moons to prodigious tidal forces, rhythmically kneading their interiors and liberating heat through friction. That tidal energy could sustain subsurface liquid water even when the moon passes through the coldest arc of the orbit, far from the warmth of the host star. Aniket Sanghi captured the historical weight of the finding. If confirmed, this would mark a new benchmark for direct exoplanet imaging. Among all worlds directly photographed to date, this would be the closest to its host star ever resolved. It is also the closest in temperature and age to the giant planets of our own solar system, and the nearest of all directly imaged worlds to Earth. The planet's very existence challenges our frameworks for understanding how worlds assemble and survive in binary environments. Alpha Centauri b orbits near enough to disrupt planet formation around Alpha Centauri a. Simulations show that giant planets in such systems either complete their formation rapidly, before the binary's gravity dismantles the protoplanetary disk, or they migrate inward from more distant formation sites. S1 likely coalesced, beyond the snow line, where water ice could contribute to solid accretion, and then either remained in place or drifted slightly inward across billions of years. Its presence raises a disquieting question. If a Saturn mass giant sweeps through the habitable zone, what became of any rocky worlds that might have taken shape there? Gas giants and terrestrial planets do not share orbital territory in peace. The giant's gravitational reach generates mean motion resonances, orbital intervals where smaller bodies' periods synchronize with the giant's in simple integer ratios. Any rocky planet drifting into a resonance acquires progressively higher eccentricity over millions of years, until orbital crossings with neighboring bodies produce collisions or ejections. Think of it as a bowling ball launched through a carefully arranged set of pins. The ball need not strike each pin individually. The first pins to scatter sideways cascade into the rest. S1 would act precisely this way, even if it never made a direct gravitational encounter with a rocky planet. Its long-range perturbations would eventually destabilize every terrestrial body in its neighborhood. Simulations of planetary architectures in binary systems show that super-Earth and sub-Neptune formation is substantially suppressed when the binary separation falls below 100 astronomical units. Alpha Centauri A and B orbit between 11 and 36 astronomical units apart, well within that suppression regime. Any rocky planets assembling around Alpha Centauri A would face gravitational harassment from two directions simultaneously. Alpha Centauri B pulling from outside, and S1 perturbing from within the habitable zone. The probable outcomes: either terrestrial planets never formed within the habitable zone at all, or they did form and were dispersed long ago. Some may have been driven into the star. Others could have been hurled into interstellar space, rogue wanderers with no parent star. A few may have been nudged outward, into colder, distant orbits where they froze. One alternative scenario remains: moons. If S1 carries substantial satellites, those bodies orbit the planet rather than the star directly, sheltered within the planet's gravitational sphere of influence. The eccentric planetary orbit would subject those moons to enormous cyclic tidal forces, flexing their interiors rhythmically and converting that mechanical energy into heat. The thermal output could maintain subsurface oceans in a liquid state even when the moon traverses the coldest arc of the orbit, far from any meaningful stellar irradiation. Saturn has Titan. Jupiter has Europa and Ganymede. All three harbor more water than Earth's entire surface supply, locked under ice or dissolved within dense atmospheric columns. If S1 hosts comparable satellites, they might be habitable despite orbiting a gas giant rather than a star directly. We have no capability yet to detect exomoons. They are too compact, too dim, too geometrically close to their host planets for any existing instrument to resolve. But the physics permits their existence. The habitable zone around Alpha Centauri A may therefore not be empty. It may simply be occupied by the wrong category of world. A gas giant where rocky planets should be, attended by moons rather than populated by continents. A cosmic bowling lane where the pins were scattered billions of years ago. The destinations where life should emerge are often the precise locations where life was never permitted a foothold. Picture a world where the continents themselves are fashioned from diamond and the mountain ranges sparkle with silicon carbide beneath the glow of a golden star. It sounds magnificent, like something conjured from speculative fiction, and it would be entirely, irrevocably dead. Diamond ranks among the hardest materials the universe produces, and that hardness is precisely the problem. Hard substances do not flow. They do not convect. They do not participate in the slow, planetary churning that keeps worlds geologically alive and atmospherically refreshed. On Earth, the mantle behaves as an extraordinarily viscous fluid on geological timescales. Heat ascending from the core establishes convection currents. Hot material rises, cool material descends. This circulation drives plate tectonics at the surface. Plates diverge at mid-ocean ridges. They converge and subduct into trenches. Volcanoes breach the crust. Earthquakes redistribute stress. Material cycles continuously between the planet's interior and its surface. A carbon-enriched planet with a diamond mantle would sustain none of this. Diamond's viscosity is high enough that mantle convection would decelerate to a halt. The crust would rigidify into a single massive shell. Geologists call this configuration a stagnant lid. Mars possesses one. Venus almost certainly does. Mercury unambiguously does. None of those bodies sustain plate tectonics. None have mechanisms to recirculate material between surface and interior. The thermal conductivity worsens everything. Diamond transmits heat 5 times more efficiently than silicate rock. Heat drains from the planetary core into space far faster than on Earth. Within a few billion years, perhaps less, the planet cools into a rigid, geologically inert sphere. Once the mantle solidifies, volcanism ceases. Outgassing stops. The atmosphere loses its replenishment mechanism. Without plate tectonics, there is no carbon-silicate cycle. Atmospheric carbon dioxide dissolves in rainfall. Rain weathers exposed rock into carbonates. The carbonates accumulate on the surface permanently, with no subduction to carry them back into the interior, no volcanism to release them back as gas. The atmosphere is progressively stripped of greenhouse gases. Without them, the planet freezes solid, unless it began with an overwhelmingly thick carbon dioxide blanket, in which case it bakes like Venus, because nothing removes the excess. No mantle convection means no magnetic dynamo. Earth's field originates from liquid iron convecting through the outer core, generating electrical currents that sustain the magnetosphere. A stagnant lid world has no core convection, no dynamo, no protective field. Stellar wind strips its atmosphere molecule by molecule across billions of years. Alpha Centauri A already carries 25% fewer heat-producing radioisotopes than our solar system. Uranium, thorium, potassium, the slow-decay elements that maintain planetary interiors at life-permitting temperatures across geological time. Begin with reduced internal heat. Lose it faster through elevated thermal conductivity, and you produce a world that becomes geologically dead ahead of schedule. A diamond world would glitter brilliantly from orbit. No cloud cover to scatter light, no tectonic relief to roughen the surface, just smooth, crystalline plains reflecting starlight in every direction. It would be a monument to geological inertia, a museum exhibit of what planetary chemistry might have produced if only the elemental proportions had fallen differently. The most visually spectacular planets might simultaneously be the most inhospitable to life. Splendor and habitability do not reliably coincide. Occasionally, the cosmos assembles marvels that are constitutionally incapable of ever awakening. The question has nagged planetary scientists for years. If the majority of rocky exoplanets sport stagnant lids, does that imply we are cosmically isolated by default? Earth is the anomaly. Most rocky bodies in our own solar system, Mars, Venus, Mercury, carry thick, immobile crusts with no plate tectonics, no functioning carbon cycle. If that pattern reflects the galactic norm rather than the exception, and if operating carbon cycles are prerequisites for sustained habitability, then genuinely Earth-like worlds may be exceedingly rare. Recent computational models, however, suggest the picture is more nuanced than a simple binary. Research teams led by Dr. and Nicola Tosi at the DLR Berlin Institute of Planetary Research ran integrated simulations coupling interior thermal evolution, volcanic degassing, and climate system feedbacks. They discovered that under specific conditions, stagnant lid planets can sustain habitable surface environments for billions of years. The enabling mechanism is volcanic outgassing during the initial several billion years of the planet's thermal history. Even absent plate tectonics, partial melting in the upper mantle can vent water vapor and carbon dioxide to the surface through episodic volcanism. If the planet begins with appropriate mantle water content, between 34 and 1,000 parts per million, and appropriate oxygen fugacity, a measure of the rock's oxidation state, degassing can construct a stable, temperate atmosphere. The habitable zone for stagnant lid worlds is narrower than for tectonically active planets. It depends sensitively on the cumulative volcanic outgassing rate. Too little degassing, and the planet freezes. Too much, and a runaway greenhouse installs surface pressures exceeding 100 bars of carbon dioxide, hot enough to boil water even at extreme pressure. Between these limits, there is a workable range where surface temperatures stabilize between water's freezing and boiling points. The complication is duration. Volcanism on stagnant lid worlds terminates after several billion years, as the interior temperature drops below the melting threshold and solidifies. Once volcanism stops, atmospheric replenishment ceases. Carbon dioxide becomes locked in surface carbonates. Water is lost to space or absorbed into crustal minerals. The planet enters terminal glaciation. Tosi and collaborators concluded that stagnant lid worlds can sustain habitability across geological timescales, but that rigorous characterization requires simultaneous modeling of interior evolution, volcanic degassing, and climate response. The bottom line, habitability is possible, but the permissible parameter space is narrow, and the boundary conditions are exacting. For the Alpha Centauri system specifically, the prospects are sobering. Fewer radioisotopes means a diminished thermal reservoir. Elevated carbon content means faster thermal drainage. Both factors accelerate the timeline to geological death, compressing the window during which volcanism can maintain an atmosphere and moderate a climate. But compressed does not mean absent. Life on Earth emerged within the first billion years of the planet's existence. If comparable timescales apply elsewhere, a stagnant lid world orbiting Alpha Centauri could sustain life for 2 to 3 billion years before locking into permanent glaciation. That is sufficient time for microbial ecosystems, potentially sufficient for simple multicellular organisms, almost certainly insufficient for intelligence to evolve, almost certainly insufficient for technological civilizations to emerge and persist. The universe may be populated by worlds that flickered into biological activity and then went silent. Planets that seized their geological window, flourished briefly by cosmic standards, and then surrendered to the cold when their interiors solidified. Biospheres fossilized in stone, waiting for someone to unearth them and ask what might have been. Sometimes the most heartbreaking possibility is not that life never arose. It is that life rose and then extinguished, leaving no successor to carry the memory forward. Proxima Centauri ought to be calm by now. At 4.88 billion years of age, it is nearly contemporaneous with our own solar system. This tiny red dwarf has had eons to settle into the tranquil stability of stellar middle age. Stars of this type burn with extraordinary patience, living for trillions of years, their hydrogen reserves stretched across timescales that dwarf the entire history of the observable universe so far. One might reasonably expect that after nearly 5 billion circuits of the galactic center, Proxima would have finally composed itself. That expectation is catastrophically wrong. This star is a predator disguised as a quiet ember. The magnetic field is the first tell. 600 Gauss, perhaps 750 on particularly turbulent days. Our own Sun maintains roughly 1 Gauss. Proxima's field is 600 times more powerful, coiled and compressed like steel cable wound under impossible tension. These magnetic flux tubes snake through the stellar atmosphere, accumulating energy the way a drawn crossbow stores the potential for violence. When they destabilize and reconnect, they discharge that stored energy instantaneously. We call these releases super flares. The name falls short of conveying the reality. During one documented event in March 2017, Proxima brightened by a factor of 1,000 within 10 seconds. Consider what that means for any hypothetical world in orbit. Your star becomes 1,000 times brighter than normal in the time it takes to exhale once. 10 seconds. That is the interval. The universe provides any hypothetical observer to register that their environment is being annihilated. These superflares are not rare aberrations. They occur multiple times daily. The smaller events merely double or triple the star's output. The civilization-ending eruptions are less frequent, perhaps weekly, perhaps monthly. The population statistics are still accumulating, and each new observational dataset delivers worse news than its predecessor. The energy released during a major superflare can reach 10 to the 38th ergs. That figure is meaningless without context. Proxima's routine outbursts release 10 to 100 times more energy than the most violent eruptions our own Sun has ever produced. Proxima b absorbs 400 times the X-ray irradiance that Earth receives. 400 times, and that is the baseline, the ambient radiation environment during the star's quietest intervals. During active flare sequences, that figure surges further. The ultraviolet flux sits at 30 times Earth's equivalent exposure even during calm periods. A hypothetical observer on the surface of Proxima b, equipped with a UV dosimeter during a moment of relative stellar tranquility, would watch the instrument trigger every alarm threshold ever calibrated for Earth organisms. The flares arrive with companions, coronal mass ejections, titanic magnetized plasma bubbles erupt from the stellar chromosphere and accelerate outward at millions of miles per hour. When these plasma walls collide with a planetary atmosphere, they do not simply irradiate. They physically displace atmospheric molecules, dragging them upward and accelerating them past the planet's escape velocity. They peel the atmosphere away like removing coats of paint from a wall, layer by layer, molecule by molecule. This has been happening for 4.88 billion years. Every day, every week, every month, without pause or mercy. Proxima b, orbiting just 4.5 million miles from this sustained violence, has been subjected to nearly 5 billion years of uninterrupted cosmic bombardment. The planet completes 32 full orbits in the time Earth completes one. 32 transits through the stellar firing range per year we count. Multiply that frequency across billions of years, and the cumulative exposure becomes numerically incomprehensible. This is the closest potentially habitable planet to Earth, our nearest neighbor within a habitable zone. The world that science fiction imagined for generations before we confirmed its reality. And it orbits a star that makes our own space weather resemble a gentle spring shower. The star wears its age deceptively well, burning fiercely and unrepentantly, a red dwarf that refuses to mellow with time. What survives nearly 5 billion years of such unrelenting assault? The flares are only the opening chapter. Behind every burst of light and radiation comes something worse. The stellar wind flowing from Proxima Centauri moves 500 to 2,000 times more forcefully than the gentle particle stream emanating from our own sun. The contrast is between a hurricane and a whisper. This wind carries charged particles, protons, and electrons, hurling them into whatever lies in their path at hundreds of miles per second. When they intercept a planetary atmosphere, they do not ricochet, they excavate. The clinical terminology is atmospheric erosion. The underlying reality is far less antiseptic. Imagine watching waves dismantle a sandcastle on a beach. Each successive wave removes another handful of material, grain by grain, until no trace remains of what was built there. Proxima b has been standing in that interstellar surf for 5 billion years. Researchers ran the numbers. They assembled computational models of what occurs when a planet sits this near to a star, this volatile with a stellar wind, this powerful. The results returned measured in planetary ocean equivalents. 21 times the water content of Earth's oceans could have been stripped to space over the system's lifetime. 21 complete oceans, each as vast and deep as the combined Pacific, Atlantic, and Indian, all of it atomized and carried away. Hydrogen separated from oxygen, the lighter element bleeding off into the void while the heavier one remained behind. Nitrogen fares no better. Models project that up to 100 bars of nitrogen atmosphere could have been removed through ion pickup, a process by which the stellar wind's embedded magnetic field acts as a comb dragging through the upper atmosphere, catching ionized gas and accelerating it beyond escape velocity. Bar by bar, year by year, the sky bleeds away into interstellar space. The planet may have possessed every prerequisite at its origin: water, atmosphere, appropriate surface temperature, all the raw ingredients that chemistry requires to pursue biology. Then came 5 billion years of unrelenting stellar violence. The earliest phase was the most brutal of all. Young red dwarfs burn hotter and flare far more frequently than their mature counterparts. Proxima spent its first 169 million years substantially more luminous than it is today. During that interval, any surface water would have undergone runaway evaporation. Scientists designate this the runaway greenhouse phase. Between 3 and 10 ocean equivalents of water probably vanished during that opening period alone. Whatever survived now persists in the crosshairs of ongoing bombardment. Without a shielding magnetic field, the atmosphere has no defense against the charged particle storm. Earth's magnetosphere deflects the solar wind around our planet, channeling it along field lines that carry it harmlessly into space. Proxima b may lack that luxury. Tidal locking could suppress the planetary dynamo that generates magnetic fields. No differential rotation between core and mantle. No liquid metal churning in the geometrically correct configuration. No field, no protection. The star operates without consideration for evolutionary timescales. It does not wait for chemistry to develop adaptive responses. It simply strips away what it can reach. Photon by photon, particle by particle, atmospheric layer by layer. The evidence is visible in our own solar system. Mars forfeited most of its atmosphere billions of years ago when its intrinsic field collapsed. Venus may have surrendered oceanic inventories of water. Even Earth sheds atmospheric particles at its magnetospheric boundaries, though slowly, protected by both its field and its distance from the Sun. Proxima b orbits 8 times closer to its star than Mercury orbits ours, and Proxima is 600 times more magnetically violent than our Sun. The arithmetic is pitiless. If Proxima b began with everything necessary for life, it may now have nothing. If it began with nothing, the stellar wind guarantees that condition endures. The erosion mechanism runs without ceasing, without rest, without any accommodation for the world locked within its relentless grip. Somewhere encoded in the data, buried within the scatter of measurements and the assumptions of models, lies the answer to whether anything survived, whether survival was ever mechanistically possible. Ultraviolet light destroys ozone. This is not contested science. The chemistry is understood with precision. Ozone molecules, 3 oxygen atoms covalently bonded, absorb UV photons and dissociate. Under normal circumstances, the atmosphere regenerates the molecular shield at the same rate it is being depleted. Dynamic equilibrium maintained, biological surfaces protected, the atmospheric column remaining a functional screen between living matter and the lethal spectral content of stellar radiation. Proxima b is denied that equilibrium. Every superflare from Proxima Centauri bathes the planet in a UV pulse that shatters ozone molecules by the billions in seconds. The photochemistry shifts dramatically. Ozone concentrations collapse, the protective column thins. UV radiation, no longer absorbed in the upper atmosphere, penetrates through to lower altitudes and eventually to the surface, where whatever biology might exist is attempting to persist. Earth has a recovery mechanism. Following a solar flare, the ozone column rebuilds itself across days to weeks. Photochemical reactions regenerate ozone from molecular oxygen. The shield reconstitutes itself. Life continues, largely unaware of how close it periodically comes to being exposed to damaging UV levels. On Proxima b, That recovery sequence never completes before the next superflare arrives, then another and another. During active phases, multiple superflares occur within a single day. The atmosphere exists in a state of permanent triage, attempting frantically to restore a molecular shield that is continuously being demolished. The analogy is trying to construct a building during an unrelenting storm. You manage to secure a few structural elements before the next gust tears them away. Modeling what this means over decades and centuries reveals a persistent partial depletion of the ozone column. It never achieves full density. It hovers at some fraction of a healthy shield, and that fraction governs how much UV penetrates to the surface, how much photochemical damage biological molecules accumulate, how deep into water or into geological substrates life must retreat to avoid mutational saturation. Between major superflares, years occasionally pass during which the ozone might theoretically recover towards something approaching functional protection. Then the next catastrophic event resets the photochemical clock. Any organisms that had migrated into the marginally protected surface zones encounter the unattenuated UV flux again. Natural selection operating under conditions of extreme, repetitive stress. Extinction events cycling continuously through the biosphere. Earth's biosphere required billions of years to develop UV tolerance that extends across the full range of exposed life forms. Some organisms manage UV radiation effectively. Others succumb rapidly to even modest doses. On Proxima b, the selection pressure would be simultaneously relentless and absolute. Either evolve resistance to UV intensities that would fatally irradiate most organisms on Earth, or go extinct. There is no intermediate position, no extended recovery window for diversification. The host star sets the evolutionary terms unilaterally. Deep water affords some refuge. UV penetrates only the uppermost meters of ocean. Below that depth threshold, biology might persist regardless of what transpires in the atmosphere above. Subsurface environments, cavern systems, fracture networks penetrating into bedrock, anywhere insulated from direct photon exposure, these become the only viable habitats. Life on such a world would not colonize open surfaces. It would exist in permanent subterranean retreat. Even that refuge has limits. Water shields against UV but provides no protection against X-rays, which penetrate to much greater depths. Retreating far enough to escape X-ray irradiation introduces its own constraints. No sunlight, no photosynthesis, no energetically accessible metabolic pathway based on solar radiation. Life would need to find alternative energy sources, hydrothermal chemical gradients, thermochemical reactions, energy released by radioactive decay. The list of viable metabolic strategies shrinks with each additional constraint applied. The perpetually depleted ozone layer becomes a metaphor for the world itself, a planet that never catches its breath, that never receives a respite from the ongoing assault, that exists in a state of permanent crisis where the background condition is damage, and the superflares represent damage piled on top of damage. Scientists continue debating whether such an environment could sustain life at all. The debate persists because definitive proof in either direction remains unavailable. But the ozone layer does not wait for consensus. It continues breaking. Red dwarfs constitute 75% of all stars in the Milky Way galaxy. Let that number anchor itself in your thinking. 3 of every 4 stars you can see overhead, and all the far more numerous ones invisible to unassisted eyes, are red dwarfs. They are the universe's most prolific stellar product, compact and thermally efficient, consuming their hydrogen reserves so conservatively that they will outlive every other stellar category by vast margins. Trillions of years from now, when stars like our Sun have long since exhausted their fuel and collapsed, red dwarfs will still be burning steadily. On paper, they should be the most promising venues for life in the cosmos. Their longevity provides extended periods for biological evolution. Their abundance supplies maximum statistical opportunities. Their habitable zones sit in close proximity to the star, making planets far easier to detect and characterize. Every statistical argument points toward red dwarfs as the dominant hosts of life in the galaxy, except for one categorical problem. They are violent. Proxima Centauri is not an unusual specimen. It is representative. Most red dwarfs flare. Most sustain magnetic fields enormously more powerful than our suns. Most generate stellar winds that dwarf the gentle particle stream we bathe in. The activity intensity varies among individuals, but the pattern holds across the population. Red dwarfs remain magnetically active throughout their entire lifetimes. Unlike more massive stars that gradually calm with age, red dwarfs stay restless. Tidal locking is an inevitable outcome at these orbital distances. A planet within the habitable zone sits so near its star that gravitational forces synchronize its rotation with its orbital period. One hemisphere permanently exposed, one hemisphere permanently shielded. The sunlit face might sustain habitable temperatures. The dark face freezes. The terminator zone separating them becomes the only geographic region where liquid water could conceivably persist. But tidal locking may simultaneously suppress the planetary dynamo that generates magnetic shielding. Earth's magnetosphere derives from our planetary rotation combined with liquid iron convecting through the outer core. Lock the rotation, and the dynamo may cease operating. No field means no protection against stellar wind. The atmosphere erodes. The planet dies. Even supposing the planet somehow retains both a functional magnetic field and an intact atmosphere, biology still confronts a foundational obstacle. The flares do not stop. Billions of years of sustained stellar violence. Ozone columns that never fully reconstitute themselves. UV and X-ray irradiance at levels that would render Earth's surface sterile within days. The barriers facing biological establishment accumulate faster than any plausible adaptive response can surmount them. Some researchers argue that life is a sufficiently robust and creative process to adapt. Given adequate time and sustained selection, pressure, organisms might evolve extreme UV tolerance, construct thick biological shielding, or establish permanent subsurface ecosystems. Life on Earth survives in boiling sulfurous acid springs, in repositories of highly radioactive waste, in the crushing pressures of deep-sea hydrothermal vent systems. Perhaps biology around red dwarfs is simply organized differently than we can currently envision. Other researchers redirect attention to the observational record. We have no evidence of life anywhere in the universe except on Earth. 0 confirmed detections after decades of systematic searching. If 3/4 of all stars are hostile to biology, and the remaining quarter is dominated by short-lived massive stars and dynamically challenging binary systems, what fraction of the galaxy actually provides viable conditions for life? The cosmos might be substantially more sterile than our optimistic default assumptions have presumed. The paradox is genuinely disorienting. The most common stars in the universe may be the least hospitable to life, The stellar environments where planets are most readily detected and characterized may be precisely the environments where biology is least likely to gain a foothold. We are profoundly biased by our own origins. We evolved in orbit around a star representing only a minority of stellar types. What if our situation is the anomaly rather than the template? This matters far beyond the confines of academic debate. It fundamentally reshapes every calculation we make about the probability of finding life elsewhere. Drake equation estimates that produce optimistic tallies of communicating civilizations assume that habitable planets are abundant. If dwarf systems are systematically excluded from the inventory, the count of genuinely habitable worlds drops dramatically. The galaxy could harbor trillions of planets and remain mostly biologically empty. Proxima b sits within the habitable zone by the temperature criterion. It satisfies the temperature requirement. But temperature is one variable among dozens. Stellar activity level, atmospheric retention capacity, magnetic field strength, tidal locking geometry, superflare frequency, chronic radiation environment. Each variable acts as an independent filter. Each filter removes additional candidates from the list of genuinely habitable worlds. By the time every applicable constraint has been applied, the roster of environments where life could plausibly persist may be vanishingly short. 3/4 of all stars eliminated on the basis of violent activity. Most of the remainder eliminated for various additional reasons. What survives every filter? Perhaps a universe far more solitary than we have permitted ourselves to hope. We define the habitable zone through temperature arithmetic. The calculation is clean and tractable. Take a star's luminosity. Calculate the orbital distance at which an orbiting planet receives sufficient energy to maintain liquid, water at its surface. The result marks the zone's inner and outer boundaries. Too close and oceans boil away. Too distant and they freeze. Within those boundaries, life as understood from Earth might arise. The formula is compact enough to fit in a line of algebra. Proxima b sits squarely centered in that zone. Geometrically ideal placement. By the strictest textbook definition, this planet occupies one of the most favorable positions in our immediate cosmic neighborhood for habitability. The equilibrium temperature works out to roughly 234 Kelvin. Cold by Earth standards, but workable. With appropriate atmospheric composition and greenhouse gas loading, surface temperatures could climb into the liquid water range. Everything appears to add up cleanly until you begin incorporating the additional variables. Then the calculation disintegrates. Temperature is necessary for habitability, but nowhere near sufficient. A planet requires an atmosphere, and not just any atmospheric mixture. It needs the right molecular inventory at the right partial pressures. Too sparse and the surface freezes despite lying within the thermal habitable zone. Too dense and runaway greenhouse effects convert the world into a pressure cooker hell. The balance is delicate, and the permissible range is narrow. Proxima b confronts stellar wind 500 to 2,000 times more forceful than Earth experiences. That wind strips atmospheric gas continuously. Whatever inventory the planet initially accumulated is under unrelenting assault. Superimpose the flares, the X-ray and UV bombardment, and the magnetic field interactions, and the net atmospheric loss rate accelerates beyond what any plausible supply mechanism can offset. The planet may be entirely airless today. Every temperature-based habitability calculation presupposes that an atmosphere exists. Strip that assumption away. and the habitable zone framework collapses entirely. Tidal locking introduces independent complications. Even if an atmosphere survives intact, even if global circulation successfully redistributes thermal energy from the illuminated hemisphere to the dark one, you still confront a world where half the planetary surface never receives direct photons from its star. Photosynthesis is geometrically impossible on the night side. The Terminator corridor where day meets night becomes the only strip of terrain where anything resembling Earth-like surface biology could theoretically operate. The three-dimensional habitable zone contracts from a spherical shell to a narrow linear band. Ozone depletion imposes a further constraint. The standard habitable zone calculation assumes that UV radiation remains within biologically tolerable limits. On Proxima b, UV flux during the quietest periods already exceeds Earth's ambient levels by a factor of 30. During superflares, it climbs far beyond that baseline. Life requires either effective shielding or the ability to retreat into shielded environments. The planetary surface becomes biologically hostile regardless of surface temperature. Researchers who specialize in habitability are progressively adopting revised terminology. The classical temperature-based habitable zone is recognized as too optimistic, applicable only as a first approximation. The community increasingly invokes a continuously habitable zone that integrates stellar activity history, atmospheric retention probability, and long-term environmental stability. This revised zone is substantially smaller. For M-dwarf stars like Proxima, it may not meaningfully exist. A member of the original discovery team has acknowledged that the case against habitability is not conclusively proved. This is technically accurate. We do not possess direct measurements of Proxima b's atmosphere or surface conditions. We cannot assert with absolute certainty that life is impossible there. Absence of evidence is not evidence of absence, and science demands appropriate epistemic humility. But every line of evidence available points consistently in one direction. Each new study adds another barrier. Each modeling effort generates additional reasons why biology would struggle to gain purchase. The cumulative weight of unfavorable evidence grows heavier with every passing year of investigation. At some point, the burden of proof shifts. The central question evolves from whether the planet is habitable to whether the word habitability retains any useful meaning in such a physical environment. We wanted our nearest neighbor to be welcoming. We wanted the closest planet in a habitable zone to actually be habitable in some meaningful sense. The universe has no investment in accommodating that desire. It operates according to physics and chemistry, indifferent to human aspirations. Proxima b may technically qualify for the habitable zone on thermal grounds. By virtually every other relevant metric, it occupies a killing field. The distinction is consequential. We will spend decades directing observations toward this world, probing its atmosphere if one exists, searching for biosignatures if any can be detected. The investment is scientifically justified because proximity makes the search operationally feasible. But the habitable zone containing Proxima b may be habitable in name only, a mathematical convenience, a cosmically ironic joke at the expense of anyone who thought distance from a star was the primary variable determining where life could survive. Stephen Hawking stood before an assembled press in April 2016 and declared that humanity would go to the stars. Not someday, not in some indefinitely deferred future after all engineering obstacles have been resolved, within a generation. Alongside Russian billionaire Yuri Milner, he unveiled Breakthrough Starshot, a $100 million initiative to dispatch spacecraft to Alpha Centauri at 20% the speed of light. The probes would reach their destination in 20 years. Your children could live to receive imagery from another star, system. The announcement had the quality of a thunderclap. The physics are brutal and magnificent simultaneously. Accelerate a spacecraft to 134 million miles per hour. Traverse 25 trillion miles in 2 decades. Accomplish this using technology buildable today, not propulsion systems imagined in science fiction. The only viable path is to make the spacecraft absurdly small and drive it with photon pressure. Enter the nanocraft. 1 gram of total mass equivalent to a paperclip. Within that gram you must fit cameras, inertial navigation, power generation, a communication laser, computational processors, everything a conventional probe carries, miniaturized until mass itself becomes nearly irrelevant. The entire payload weighs less than a sugar cube. The light sail performs the seemingly impossible acceleration. 4 meters on each side, fabricated from silicon nitride just 200 nanometers thick, perforated by billions of precisely engineered holes arranged in a pattern computationally optimized by neural networks. The holes convert the sail from transparent to reflective. 99% of incident laser photons bounce off rather than passing through. That 1 percentage point of difference determines whether the mission is physically achievable. A ground-based laser array spanning 1 square kilometer, delivering 100 gigawatts of coherent power, fires at the sail continuously for 10 minutes. 10 minutes of sustained acceleration at forces reaching 10,000 times Earth's gravity. Those forces would reduce any human body to a smear in an instant. The nanocraft, constructed with no moving parts and nothing structurally capable of failing, survives. At the conclusion of those 10 minutes, the probe is traveling at 20% of light speed. The laser array powers down. The nanocraft coasts for the remainder of the journey. 20 years later, it arrives at Alpha Centauri. The flyby lasts minutes. No deceleration is possible. No fuel reserve exists for braking. The probe screams through the system at 134 million miles per hour. Its instruments capturing data as rapidly as physics permits during the brief passage. Then it continues into the interstellar medium beyond, leaving the system behind forever. 4 years after the flyby, the first signals arrive on Earth. The data stream crawls across 25 trillion miles at light speed. Images, spectroscopic measurements, magnetic field readings, everything the probe's instruments registered during its minutes in the Alpha Centauri system. A child born on the day of launch would be 24 years old when those first images appear on Earth. Old enough to have started a career. Old enough to have children of their own. Old enough to have nearly forgotten that the mission existed. The engineering obstacles are staggering in their scope. Maintaining the sails centered on the laser beam throughout the acceleration phase demands metasurface properties that passively self-correct the pointing geometry. Surviving collisions with interstellar dust at 20% light speed demands materials science not yet fully developed. Transmitting data across 4 light-years using a laser powered by solar panels collecting light from a star. 4 light-years away, demands that the same kilometer-scale laser array that launched the probe reconfigure to function as a receiver. Yuri Milner provided the seed funding. Stephen Hawking contributed his name and his intellectual authority. The project assembled international teams to rigorously assess feasibility across every engineering domain. Years of study followed: materials characterization, component testing, prototype fabrication, simulation. The conclusion: achievable, difficult, expensive, contingent on sustained international coordination across decades of development, but fundamentally achievable. Not science fiction. A legitimate engineering program with no obvious showstopper and with viable solutions visible on the developmental horizon. Phase 1 concluded in 2025 with $100 million expended on feasibility studies. The results are being documented. The project is currently on pause while organizers pursue the substantially larger funding needed for Phase 2. That phase requires billions. Prototype laser array construction, full-scale sail testing, in-space demonstration of core technologies before committing to the full interstellar mission. No certainty that the required funding materializes. No certainty that Phase 2 is ever initiated. Breakthrough Starshot could remain an inspiring technical concept that never transitions from paper to hardware. But for one electrifying moment in April 2016, standing alongside one of the most consequential scientific intellects of our era, humanity formally announced its ambition to reach another star. The dream may ultimately prove unreachable. Then again, half a century ago, landing humans on the moon was also described as impossible. The light sail was always the critical bottleneck. The specifications are unforgiving. 4 meters square, lighter than any feather, reflective enough to bounce back 99% of incident laser energy, strong enough to survive 10 minutes at 10,000 G without structural failure. The material must approach perfection. A single manufacturing defect, a single zone of structural weakness, and the sail tears apart under the laser's pressure in the first seconds of acceleration. Using the fabrication techniques available before 2025, constructing a single sail would have consumed 15 years and cost over 200 billion euros. Those economics rendered the mission concept economically non-viable before it ever left the conceptual stage. Then, in 2025, a research team led by Professor Norte demonstrated something that transformed the landscape entirely. They fabricated a complete, full-scale light sail in a single day using optical lithography. Not a scaled prototype, not a representative test section, but an actual 4 meter by 4 meter sail possessing all the required optical and mechanical properties. The cost per sail dropped to approximately 25 million euros, a reduction of nearly a factor of 9,000 in price. The 15-year fabrication timeline compressed to 24 hours. The technique is conceptually elegant but operationally demanding at an extreme level. Optical lithography uses structured light fields to pattern materials at nanometer scales. The semiconductor industry has exploited it for decades to manufacture integrated circuits. Norte's group adapted the methodology to produce a silicon nitride membrane 200 nanometers thick, perforated with billions of nano-sized holes arranged in a pentagonal lattice optimized computationally. The holes are the critical innovation. Light impinging on a solid surface reflects, refracts, or is absorbed, with most of the energy converted to heat. Thermal loading destroys the sail. The hole array creates a photonic crystal structure that reflects incident radiation through destructive interference. 99% of laser energy bounces back, the remaining 1% spreads diffusely across the full sail structure at intensities the material can tolerate without failing. The overall temperature remains manageable. The sail survives the acceleration pulse. Neural networks were employed to optimize the complete hole geometry. The shape is not regular, not circular or hexagonal, but a complex potato-like contour for each aperture, dimensioned and positioned to simultaneously maximize reflectivity and minimize total mass. This pattern repeats across billions of holes spanning 4 square meters of membrane. A single fabrication error propagates through the entire structure, corrupting the interference pattern and degrading reflectivity. Prior approaches relied on electron beam lithography, a serial technique that inscribes patterns sequentially, analogous to drawing with an exceptionally fine stylus. The approach achieves extraordinary positional accuracy, but requires 15 years to complete one sail. The enabling insight was transitioning to optical lithography, which exposes entire pattern sections simultaneously using precision light masks. What required 15 years now takes a single working day. The economic implications are transformative. 25 million euros per sail is expensive by ordinary standards, but manageable. A private individual of substantial means could fund one sail. A small nation's space program could commission several. A governmental consortium could underwrite a complete mission carrying multiple redundant probes at a cost that falls within the range of major international scientific programs. The economics shift from impossible to merely challenging. Serial production becomes a realistic prospect. Fabricate one sail per day, and within months you possess enough for initial testing campaigns. Within a year, enough for a full mission deployment sequence. Launch probes in staged succession toward different targets. Alpha Centauri first, then Barnard's star, then other proximate systems. Distribute the mission risk across multiple destinations. The 2025 announcement generated less public attention than it warranted. No high-profile personalities at the podium. No primetime press event. Just a peer-reviewed technical paper demonstrating the fabrication methodology and the accompanying cost analysis. The research community immediately grasped the implications. Breakthrough Starshot, paused after completing Phase 1, had just become economically viable. Open questions remain. The sail functions under laboratory conditions, but can it survive launch stresses? Deploy correctly in orbital vacuum? Maintain structural integrity through 10 minutes of 10,000 G laser acceleration? Survive multiple dust grain impacts at 20% light speed? Each question demands experimental answers. Each experiment demands funding. The development pathway from laboratory demonstration to flight-ready hardware spans years at minimum, probably decades. Demonstrating the concept on paper is the first milestone. Building flight-qualified hardware is the second. Validating performance in space is the third. Executing the full interstellar mission is the fourth. The sequence cannot be compressed arbitrarily. Space systems engineering is unforgiving of shortcuts. A single overlooked failure mode destroys the mission, and with it, any chance of a second attempt. But the critical bottleneck is broken. The fabrication economics that previously made the concept unachievable are no longer prohibitive. The 15-year manufacturing timeline that made the mission a multi-generational commitment has collapsed to a single day. Breakthrough Starshot remains on pause pending funding decisions. But the nature of that pause has changed. Somewhere in funding negotiations, in boardrooms where governments and private investors weigh cost against scientific return, a determination will eventually be made. continue or cancel, commit resources or walk away. For now, the light sails rest on laboratory tables, gossamer thin, nearly invisible when viewed edge-on, waiting for humanity to decide whether the aspiration to reach the stars is something we will act upon or merely something we enjoy describing. 20 years sounds like a manageable interval. Launch a probe today and it arrives at Alpha Centauri while your children are completing their university educations. Allow 4 more years for the return signal, and you are still young enough to witness the data. 24 years total. Less than a human lifetime, and barely longer than the interval the Voyager probes have been traveling since their 1977 launches. A span comprehensible within a single generation's sustained attention. But 20 years is merely the surface complexity of the mission. The laser operates for 10 minutes, accelerating the nanocraft from rest to 20% of light speed. Those 10 minutes demand the largest coordinated laser installation ever constructed. 100 gigawatts of aggregate power, 1 square kilometer of precision focusing optics, every element operating in phase-coherent synchronization. Any component out of synchronization tears the sail. The spacecraft experiences 10,000 g of acceleration, 10,000 times the gravitational pull at Earth's surface. A human body would be instantaneously liquefied. Even hardened electronics must be engineered to survive forces that would shatter the frames of conventional spacecraft. Every component must be solid state. No moving mechanical elements, no liquid cooling, no connectors or fasteners susceptible to failure under loading. The entire probe is fundamentally a single piece of layered, engineered material with sensors and processors embedded throughout its structure. After those 10 minutes, acceleration ceases. The probe is moving at 134 million miles per hour and has already covered 1 million kilometers. The laser array shuts down. From that instant forward, the journey is purely ballistic. 20 years of free flight through the interstellar medium with no course correction capability, no propellant reserve for trajectory adjustment, no mechanism for decelerating at the destination. The nanocraft must be aimed precisely at the outset. Mission engineers must predict where Alpha Centauri will physically be in space 20 years hence, accounting for the system's proper motion, accounting for Earth's position in its orbit at the launch epoch, accounting for gravitational perturbations from every massive body along the trajectory. The launch geometry determines everything downstream. An angular error of a fraction of a degree at departure translates to a positional miss of trillions of miles at arrival. Interstellar space is not empty. Diffuse dust grains, atomic hydrogen, cosmic ray particles, all of it strikes the probe at 20% light speed. Even a particle of sand carries bullet-like kinetic energy at that velocity. The sail must tolerate repeated impacts without structural failure. The electronics must be shielded against radiation damage. Mass budget constraints make redundancy impossible at 1 gram total mass. There is exactly one chance to succeed. Communication across 25 trillion miles requires an engineering marvel. The probe carries a miniature laser powered by solar panels that can only generate useful power when the spacecraft is in close proximity to a star. During the brief minutes of the Alpha Centauri flyby, the nanocraft must orient itself correctly, activate its laser, and begin transmitting all recorded data back toward the solar system. 4 years later, that signal reaches us. The same kilometer-scale laser array that launched the probe must be reconfigured as a photon collector. The incoming signal is unimaginably attenuated. Individual photons that departed Alpha Centauri made the 4 light-year crossing one by one, distributed across the detector aperture. Advanced photon counting techniques and signal processing algorithms laboriously reconstruct the transmitted data from that trickle of arriving light. The images assemble themselves gradually, 1 pixel at a time, as the transmission continues over weeks or months. A child born the day the mission launches grows up with the mission as background context. Elementary school years unfold while the probe crosses the first few light years. High school graduation occurs somewhere near the halfway point. University, a career's beginning, perhaps parenthood, and then the signal arrives. The person is 24 years old. The mission that existed from the day of their birth finally delivers its opening chapter of results. This scenario assumes flawless execution throughout. 1 failed component, and the entire mission fails. 1 calculation error, and the probe sails past the Alpha Centauri system into endless interstellar darkness, with no mechanism for course correction. The flyby window for observation is measured in minutes. No second orbital pass, no lingering for extended study, no opportunity to return to an overlooked measurement. Simply a 134 million mile-per-hour sprint past another star system. Researchers have noted with dry humor that the probe's entire science sequence at Alpha Centauri will conclude faster than it typically takes to write the grant applications that funded the mission's development. 20 years of transit, 4 years of signal propagation, 24 years of anticipation and patient waiting, in exchange for a few minutes of data acquisition from another stellar system. Yet those few minutes would fundamentally revise our comprehension of humanity's position in the cosmos. Visual imagery of Alpha Centauri's planets, if any exist. Spectroscopic characterization of their atmospheric compositions. Definitive evidence for or against habitability, or at minimum toward sterility. Answers to questions humanity has been formulating since we first understood that the lights in the night sky were other suns and began wondering whether other worlds circled them. 24 years. 1 generation's investment of patience for the first direct glimpse of another stellar system. The next observational window opens in August 2026. That is not an estimate. It is a calculated prediction. Orbital simulations propagating millions of candidate trajectories for the vanishing planet converge on a specific date range. If the planet is real, if it follows the orbital geometry implied by the combined 2019 and 2024 detections, it will be positioned for detection again approximately 14 months from the current date. Positioned means displaced sufficiently far from Alpha Centauri A that the coronagraph can cleanly separate planet from star, far enough that the planetary signal emerges above the scattered light halo. The simulations express clear confidence. Fully 52% of dynamically stable orbital solutions place the planet in a detectable configuration during the August 2026 observing window. 52%, marginally better than a coin flip, but unambiguously better than chance. The planet oscillates on its eccentric trajectory, retreating close to the star where instruments go blind, then swinging back outward to where it can be seen. August is the outward swing. James Webb will point toward Alpha Centauri again, with the same instrument configuration, the same coronagraph optics, the same wavelength selection. The team will execute the same meticulous scattered light subtraction for both Alpha Centauri A and B, removing diffraction halos, speckle noise, and background gradients pixel by pixel. They will examine the sky coordinate where orbital mechanics predicts the planet should appear. Either a source emerges at the predicted location, or it does not. If the source appears where the models say it should be, statistical confidence in the detection vaults above 95%. The planet is confirmed. The orbital solution is validated. Humanity will have directly photographed a Saturn mass gas giant orbiting within the habitable zone of the nearest sun-like star to Earth. Spectroscopic follow-up becomes the immediate priority. Atmospheric composition, gas column densities, temperature profile, cloud structure, comparison with Jupiter and Saturn as reference analogs, fundamental characterization of how giant planet chemistry proceeds in a binary stellar environment. If nothing appears at the predicted location, the team returns to the beginning. Either the orbital model requires revision to accommodate more complex dynamical interactions, or the 2019 and 2024 detections were instrumental artifacts, systematic noise patterns that mimicked planetary sources convincingly enough to survive careful analysis, but that ultimately had no physical object behind them. Statistical confidence in the detection falls below 30%. The candidate joins the library of promising signals that ultimately turned out to be nothing. Or, most intriguingly, the planet appears somewhere other than where the models predicted. Shifted to an adjacent position, perturbed by gravitational influences not yet incorporated into the dynamical models, displaced by a planetary companion whose existence we have not yet recognized. That outcome would be the most scientifically rich of all. It would mean something is genuinely there, something dynamically complex, something that does not conform to simple two-body Keplerian orbital mechanics, but requires a multi-body gravitational accounting that the current models have not yet captured. The entire detection team is already in a state of active preparation. The researchers who constructed the specialized computational pipelines for handling Alpha Centauri's challenging observational geometry. The orbital dynamicists who ran millions of trajectory simulations to project where the planet would reappear. The instrument scientists responsible for maintaining JWST in optimal operational condition. The schedulers who must negotiate observation time in one of the most oversubscribed research facilities in the history of science. Everyone connected to this investigation is marking calendars. James Webb receives more observation proposals than any telescope previously operated. The competition for time is intense beyond anything the pre-JWST community experienced. Allocating time to re-examine a target already visited twice demands explicit scientific justification. The potential return must genuinely warrant the allocation. That case was made successfully. The time was awarded. August 2026 carries weight beyond a routine observing campaign. It is the decisive moment for one of the most potentially significant exoplanet discoveries of the decade. The nearest cold gas giant to Earth, if it genuinely exists. A planet within the habitable zone of a solar-type star, if the photometric detection is authentic. An unprecedented window into how planetary systems assemble and survive in binary stellar environments, if the physical interpretation is correct. Or it is nothing. A false positive, sophisticated enough to survive two independent detection campaigns, but ultimately traceable to instrumental systematics rather than a real planetary body. Science has encountered this category of outcome before. detections that generated genuine excitement and could not be reproduced, signals that vanished under scrutiny, anticipation that gave way to the quiet acknowledgement that an artifact had been mistaken for a discovery. The scientific enterprise extracts lessons from its failures as efficiently as it does from its successes. Failure and success alike refine the methodology. But failures carry their own particular sting for the individuals who invested years of effort in the search. The telescope will observe. The data will be acquired. Analysis will consume weeks to months following the observations. Peer review will extend the timeline further. Eventually, a publication will appear formally reporting the outcome. Either the planet is confirmed or it is not. Either we have found something that will rewrite the textbooks, or we have learned something important about the limits of what our current instruments can reliably detect. August 2026 approaches. The moment of reckoning advances regardless of our readiness. We have always looked toward Alpha Centauri and felt the pull of what might be waiting there. At 270,000 times the distance to our own sun, yet 100,000 times nearer than most of the exoplanet host stars we routinely study, the system occupies a unique position in our conceptual geography of the cosmos. Close enough that driving at highway speed would get you there in a mere 42 million years. Impossibly remote and tantalizingly proximate simultaneously. The paradox has persisted since the moment we first understood what stars actually are, since we grasped that the light overhead represents other furnaces rather than perforations in a celestial dome. Every telescope we have ever built has eventually been aimed at those two bright points in the southern sky: optical refractors, radio dishes, infrared satellites, X-ray observatories. We train our instruments on Alpha Centauri not because we have a specific theory to test on any given observing night, but because proximity commands it, because our nearest stellar neighbors demand investigation, because if we cannot characterize the system 4 light-years away, any ambitions to understand the system's hundreds or thousands of light-years distant are built on a foundation of ignorance. The search has consumed the working lives of multiple scientific generations. The Very Large Telescope committed 100 hours of prime observing time in 2019, driving ground-based direct imaging technology to its operational limits. James Webb surrendered irreplaceable observing hours in both 2024 and 2025. Foregoing the opportunity to train its instruments on distant galaxies, billions of light-years away, in order to scrutinize our cosmic next-door neighbor. The Nancy Grace Roman Space Telescope, scheduled to begin science operations in 2027, has Alpha Centauri listed among its primary targets from its earliest planning documents. The extremely large telescope, still under construction on Cerro Armazones in Chile, has dedicated observation programs allocated for Alpha Centauri in its commissioning phase. We cannot stop looking because our psychology does not permit us to accept permanent ignorance about the nearest point of light in the sky. The question of whether planets orbit Alpha Centauri A and B is not academic curiosity in the conventional sense. It is foundational to our understanding of where planetary systems form, and why, how stellar system architecture emerges from initial conditions, and what fraction of stellar environments across the galaxy might be genuinely hospitable to life. If metal-enriched sun-like stars in binary systems consistently fail to produce planets, that finding encodes something deep and important about the physical conditions required for planetary system formation. If such systems do produce planets, That finding demonstrates that binary stellar environments are far more accommodating to planet formation than our theoretical models have suggested. Science fiction authors have situated civilizations at Alpha Centauri for generations, long before any observational technology capable of testing the hypothesis existed. The novels, the films, the games, the entire cultural mythology of Alpha Centauri as a cradle of extraterrestrial neighbors was built before we had the tools to look. Avatar placed Pandora in the system. Countless other narratives did the same. Not because astronomers instructed fiction writers to set their stories there, but because the human narrative instinct cannot resist populating the nearest stars with life and consciousness. We are a species that creates stories. We observe the lights in the sky, and we people them with neighbors. The reality we are uncovering is simultaneously colder and more beautiful than any of those invented scenarios. Proxima b might be permanently locked, its atmosphere already stripped, its surface sterilized beyond recovery. Alpha Centauri A might harbor a gas giant on a chaotic orbit that swept every rocky world from the habitable zone billions of years ago. Alpha Centauri b might be entirely devoid of planetary companions. None of that diminishes the profundity of the act of finding out. Uninhabited worlds instruct us as richly as inhabited ones would. If the planet is confirmed in August 2026, we will have crossed a threshold that previous generations of astronomers could only fantasize about. A directly imaged exoplanet orbiting the nearest sun-like star in the cosmos. We will characterize its atmosphere, determine its mass with precision, reconstruct its orbital history, and compare its properties with the giant planets of our own solar system. The data will propagate through the scientific literature for decades. Doctoral dissertations will be constructed around individual aspects of the dataset. Theoretical models will be calibrated and refined. Our understanding of how the universe builds and arranges planetary systems will deepen in ways that are not yet foreseeable. If we find nothing in August 2026, we will have precisely delimited what is absent. We will know the boundaries of what current observational technology can and cannot detect around the nearest stellar system. We will sharpen our methods and apply them with updated techniques when the next generation of instruments comes online. The search will continue because proximity makes it the highest value target in existence. But beyond all the data, beyond the measurements and the models and the peer-reviewed publications and the conference presentations, something else is happening here that resists reduction to scientific methodology. The simple fact that we look at all, that we constructed instruments of sufficient sensitivity to detect planets orbiting other stars, that we refuse to accept permanent ignorance about what orbits our nearest neighbors, that we commit billions of dollars and decades of collective human effort to answering questions that provide no immediate material benefit, that do not feed anyone, shelter anyone, or contribute to economic productivity in any direct way. We search because we are human in the deepest sense of that word, because curiosity is woven into our cognitive architecture at a level as fundamental as the drives for nourishment and safety. Because gazing at the night sky and demanding to know what lies beyond is part of what distinguishes us from every other form of life that has ever existed on this planet. We alone formulate these questions. We alone construct the instruments capable of pursuing answers. Existing chemical rockets would require 75,000 years to reach Alpha Centauri from Earth. 3,000 human generations. Every person you have ever known, their descendants' descendants replicated 3,000 times over before the spacecraft completes its journey. The distance makes a mockery of our ambitions, yet we design missions regardless. Breakthrough starshot, fusion propulsion concepts, generation ships carrying entire communities across the interstellar medium. We imagine the crossing because imagination is the defining activity of our species. Avi Loeb has said that Alpha Centauri represents our best opportunity to answer the most fundamental question available to science, whether we are alone in the universe. He is correct, but the answer, whatever form it takes, matters less than the practice of asking. Whether the search yields life or sterility, worlds or empty orbits, the act of searching is itself the point. We look because proximity makes looking possible. We look because our nearest neighbors are 4.2 light-years away, and we are constitutionally incapable of dying in ignorance of what circles there. 14 months, until August 2026. Then we will know more than we know today. Then the questions we cannot yet formulate will begin to take shape. The search does not terminate. Every answer expands the frontier of ignorance. Every discovery illuminates 10 new mysteries waiting in the dark. And through all of it, always, we return our gaze to those 2 bright points of light in the southern sky. Our nearest neighbors in the cosmic darkness, patient and indifferent, carrying their secrets until we are finally ready to receive them. Whatever August 2026 reveals, it will mark only one chapter in a search that has no final page. The telescopes will keep turning. The simulations will keep running. New generations of scientists will inherit these questions and carry them further than we can yet imagine. We began looking toward Alpha Centauri long before we understood what we were looking at. And we will still be looking long after the answers of today have become the foundations of tomorrow's deeper questions. The stars do not hurry, neither do we.